Okay, so we wanted to review the things that are going to be on your first test. The first of these are, of course, methods of charging. Of course, we know there are 4 different methods of charging. The first one is charging by friction, and we know charging by contact or conduction, and of course, charging by induction. And then we had that 4th method, polarization, which isn't really a full-on method of charging, but it is a way that we can sort of create the effect of having something be charged. And so you'll want to review the 4 methods of charging. You need to be able to understand them and explain them. In particular, charging by induction is kind of a tricky method. It's the method where you don't actually physically transfer charge by having a charged object come into contact, but you charge an object by inducing, creating an induction of charges being separated. You induce a separation of charge, and then you ground it to send some of the charges away, and then you cut the ground, and you're left with a charged object. So you'll want to be able to explain these 4 methods of charging. That's something worth being able to do. The next big thing that we have is Coulomb's law. We know Coulomb's law is equal to F equal to K Q1 Q2 over R squared. And so there's a lot of things that we know about Coulomb's law. First, force is a vector, and so this formula is just telling us the magnitude. And remember, I told you, do not plug the SIGN signs into the charges, Q1 and Q2. Obviously, those are the charges. But rather, draw a picture and get the direction of the forces based on whether the charges are attracting or repelling one another. We know that like charges repel, opposite charges attract. And the force is always on the line separating the 2 charges. So if I have a positive and a negative charge, we know that the force is going to be attractive. Newton's 3rd law tells us that those forces are going to be equal and opposite. So if this is Q1 and this is Q2, we can say the force of 2 on 1 and the force of 1 on 2 are going to be equal and opposite, and their magnitude is going to be given by this formula. Now, we don't plug minus signs into these Q's, but rather we have a coordinate system, X and Y, and so we can say that, for example, that force is in the positive direction and that force is in the negative direction. And so if we have to do the sum of the forces, we can simply add them up as F21 plus F12 is equal to 0, and that tells us that F21 is equal to minus F12. And of course, we know that these 2 forces have to add up to 0 because of Newton's 3rd law. They're equal and opposite. Now, normally, when we do the sum of the forces like this, we break it down into x and y components, and we deal just with the magnitudes. And we use the SIGN signs to show us directions. The next big thing that we want to be able to do is forces from multiple charges. And we want to be able to apply Coulomb's law. So if I have, say, a positive charge here, and a negative charge there, and a positive charge like that, we know that we can draw the line between the 2 charges, and we can determine what direction the force is going to be. So the positive and the negative are going to attract, so that force is going to be like that. And the positive and positive are going to repel, so that force is going to be like that. We could call this 1, 2, and 3, so this would be the force of 1 on 3, and this would be the force of 2 on 3. And then we can do vector addition to get the net force, which would be F23 plus F13. And that would be the total force acting on that topmost charge. And of course, once we have that, we can draw a free body diagram, and I can take this force F23 and simply scoot it over and draw it from this origin. So this would be F23, and then I would get F13, and that would be something like that. And I have an X direction and a Y direction. And now I can do vector addition on these two things. So basically, when working this kind of a problem, here are the steps. The first step is that you want to draw the line between the charges and figure out what the angles are. And that's going to be based on what the problem is, but you're going to have that angle theta, and that might be theta 1, and you can have that angle theta, call that theta 2. Whatever you call it doesn't really matter, but you're going to need to be able to use the geometry to figure out the direction. Because we're doing vector addition, so we've got to know the magnitudes and the directions. And so the directions are going to be given by the angles. Then you're going to want to find, once you've used the geometry to find the direction, you're going to find the magnitudes. And so we're going to use the formula of Coulomb's law, Q1, Q2 over R squared. And of course, I could have a Q1, Q3 over R squared. And in each case, this R is the distance between the charges, and these would be the two charges. So I might have this distance I might call R13, I might call this distance R23, and that would go with F23 and F13. I would end up having Q2, Q3, and here I'd have Q1, Q3, and that would be the two Q's that I would have for each of these two forces. But again, basically here's the steps. Step 1, find the directions of the forces. Use the geometry in the picture. We know, for example, these guys are going to repel along the line joining them. So if you know this angle down here, for example, you can figure out that angle. Same thing down here. We figure out the direction using attraction and repulsion. We use the picture to figure out the angle, and that gives us the angles we need. And so then step 2 is to find the magnitudes using Coulomb's law. And of course, over in my free body diagram, I would have an angle here. That would be my theta 1, and this would be my theta 2. Theta 2. And so those two angles and those two magnitudes are all you need. Then what's the third step? You do vector addition. Vector addition, and that means, so I'm going to take each of these forces and use my trig to break them down into X components and Y components, and then I do my vector addition. So look back at some of the examples and some of the homeworks that we did on this, and make sure you understand the steps of how to apply Coulomb's law. Now the next big thing we want to look at is the electric field. And so we're going to have the definition of the electric field. We know that the electric field magnitude is equal to the limit as Q goes to 0 of F magnitude over Q. And that is for a positive charge. So sometimes we'll draw a little positive to remind us that this is for an imaginary positive charge. You also need to understand what the electric field is. If I have this charge here, and it could be positive or negative, there is a field surrounding it in space. So if I point to any point in space, there's a force field around it such that if I bring another charge, that charge is going to experience a force. This imaginary field is called the electric field. And in this case, we know that for a single positive charge, if I have an imaginary positive test charge right there, the field is going to be repulsive. The force would be off at that angle, and so the electric field is going to be in the same direction. Now, keep in mind, our imaginary test charge is always going to be positive, but I could bring a real charge and put it at this point in space, and that real charge could be negative. And a negative charge is going to feel a force in an opposite direction from the electric field line. That's very important to remember. So the positive charges follow the electric field lines. The negative charges feel forces that are opposite to the electric field lines. Now, if I have a charge that I have placed in an electric field, so I've got some electric field like this. There's our electric field. we know immediately that this charge is going to feel a force that is going to be along the direction of the electric field because it's a positive charge. And if that charge is free to move, it's going to accelerate. And so we can say that the sum of the forces is going to be Q times E. That's Q times E. And so the sum of the forces is equal to Q times E. And we know that according to Newton's second law, that's also going to be equal to the mass times the acceleration. So if I have a situation where I have a charge in an electric field that's accelerating, I can calculate that acceleration. I can say that the acceleration is going to be QE over m. And I'm just solving for a here, divide both sides by m. And then, if that is constant, then I can say a constant acceleration lets me use the kinematics equations, which you guys should all remember. We know v is equal to v naught plus at. We know that x is equal to x naught plus v naught t plus 1/2 a t squared. And we also know that v final squared is equal to v initial squared plus 2a delta x. And those are the three kinematics equations. So you should be able to use the kinematics equation. So I could give you a situation where there's a charged particle in an electric field and it's accelerating. I could ask you how far it moves, how long it takes to get somewhere, what velocity it has, all the kinds of things that you can deduce using these kinematics equations. So if you're a little bit rusty on the kinematics equations, you might want to just look over them before the test and remember how to use them to solve some problems. Now, another type of problems that we saw was using electric fields in statics problems, where the thing wasn't moving, but there were some kinds of balanced forces. And so we, for example, used we did an example in class where there was an electric field and there was some pendulum looking thing with a charge at the end, and so we could say that there was some force, and we would have tension, and we would have the weight, which is of course mass times the acceleration due to gravity, and we would know that F is equal to QE, and that would be in the x direction. We would know that the tension would be having an x component, Tx, and a y component, Ty. And I could, of course, write my Ty to make a triangle with an angle theta like that. And we know that Tx is T cosine of theta. Ty is equal to T sine of theta. And we can say the sum of the forces in the x direction would be equal to F minus Tx equal to 0, and the sum of the forces in the y direction would be equal to Ty minus mg, also equal to 0, and then we could solve for whatever's unknown in the problem. But those kinds of problems are perfectly fair game. And of course you had a homework problem where you had two pendulums and there was a force between them and you had to calculate the charge or something like that. So that was a similar kind of approach. These kinds of problems are, certainly fair game for the test as well. And of course we have the type of problem where you're given some charges, so I could have a positive charge, and I could have a negative charge, and I could have a positive charge over here, and we could figure out how to figure out what the electric field is at some point in space. So I might want to know what is the electric field at this point in space. And this is very similar for the type of problems where we use Coulomb's law. So if I had another charge here and I wanted to know what the force on the charge from the other three is, we've already seen how to do that, But instead, if I simply have empty space and I want to know what the electric field is, we know that the electric field for a point charge, E magnitude, is going to be KQ over R squared, where Q is the charge and R is the distance from the charge to the point in space you're looking at. In this case, this would be the point, the red here, that's the point in space. Ignore this blue scribbles. So I want to know what's the electric field there. So the rules are that this guy is the magnitude and the direction is the same direction that an imaginary positive test charge would go if placed at that location and it was free to move. So if I have an imaginary positive test charge, this guy here is going to repel him, and so there would be an electric field like that. And let me call this Q1, Q2, and Q3, and then this would be E1. That's the electric field from charge 1. And then I would have Q2. Again, we're imagining that this guy is positive here, and so along this direction the force is going to be attractive, because a positive test charge would be attracted to the negative charge Q2. And then for Q3, the force is going to be repulsive, and so that electric field is going to be like that. So we would have E2 and we would have E3. And just like we did with Coulomb's law, we can now figure out the angles, figure out the magnitudes using this formula, and then do vector addition. Now here's my warning. Do not forget to do vector addition. If you do, I will count off a lot. You have to show that you understand that these quantities are vectors. That's very important. So you find the directions. In this case, that's going to mean the angles. You find the magnitudes using the formula, and then you do vector addition. You break everything into x and y components using sines and cosines. You add them together. You add the x parts together. You add the y parts together. You get a total x component, a total y component, and then basically you're done. You can write the electric field total as some E total x in the x hat direction plus some E total y in the y hat direction. And that'll give you the complete vector. And on a test, I'm perfectly happy with that as an answer. If I ask you for the magnitude and the direction of the total electric field, you can use the Pythagorean theorem to get the magnitude, and then just use your basic trig to get the direction like we've done 100 times before. So these are some of the things that you want to make sure that you're able to do. And of course, we have the example that I told you was going to be on the test. So I just want to remind you that if we have two charges, say Q1 and Q2, how will you find where the electric field is 0? And I made a whole other video on how to find where the electric field is 0 if you have two different charges. So you want to look that up and be sure that you can do it for a positive and a negative charge, or two of the same charges, two negative charges, for example, or two positive charges. Any of those possibilities you should be able to use and figure out where is the electric field 0. In any case, I hope that this review video will help you get prepared for the test. These are the major things. Now, again, I'm not saying that these are the only kinds of problems that you're going to have on the test. You need to look over your homework, look over the examples we worked in class. All of that is fair game. But these are the main things that people seem to struggle with on the test, and so I just wanted to make sure that you look at all of these before you take the test. And so I hope this video is helpful and will help you get ready for the test, which will be coming out very soon.